Welcome back to the OpenHBI course Code of Life. Today we want to talk about reproducible research. And first of all, I'd like to introduce to you the graphical pipeline modeling, why it's important and how it works. So what will you find if you are looking into this field of data processing? You will have something like this at the top here. You have different kinds of command line tools. They all are executed stepwise, step by step. They will read from files and write to files. So most probably the throughput of these tools is limited by the throughput of the underlying storage subsystem. And again, all of these tools will be established at every site. So that means everyone is installing them, downloading them, configuring them, because you have quite a lot of configuration parameters. And then it's quite hard to exchange how does this process work and how did we get from our amino acid reads, our base pairs, all our stuff we get as input parameters to the end. This is the challenge here. What we require here is expertise for setting up the tools, configuration, error handling, and also the scalable processing is not sure. So therefore, there's a strong requirement to enable modeling, configuration, and execution to guarantee the reproducibility. So therefore, I'd like to introduce our approach to you. First of all, we have three phases and how we come from modeling to execution. Today we will talk about the modeling. You see, we have two steps here. First is the design phase. The design phase is when researchers and process experts discuss which individual steps have to be taken to transform input data to output data. And the researcher is the person who says, okay, this is the quality metric I need, this is the information you have to take care of at this point, where the process expert says, okay, these tools have to be incorporated here. All of these steps can be done graphically. Here you see it on the right-hand side. Typically, this is replacing the whole writing down command line and bash scripts now. And the researcher can even easily adapt this kind of modeling on their own by using this graphical editor. The second phase is the so-called configuration time. The configuration time is how to configure one certain pipeline for a certain experiment, for instance. You take one of the pipeline models, give some static parameters, like this is always the reference genome we want to use, or this is the quality metric we want to take care of. And then you define one certain pipeline instance, which can be then triggered by the persons in the web lab. So how does this modeling look like? So first of all, we did the following. We use a standardized modeling technique. It's called Business Process Modeling and Notation, or BPMN. And this modeling notation is typically used for business processes. You see it on the right-hand side. It's pretty easy and straightforward explained. You have these kind of bubbles, and they are referring to tasks and certain steps. And you have this beginning sign here on top, where you see the arrow starting, and here in the end you have this last mark where the process ends. We extended this kind of notation by some relevant informations like the modular structure. You can have sub-processes and all that stuff. Parallelization annotations, so you can decide explicitly which steps can be parallelized by a framework and executed in parallel. And you have the possibility to add parameters and variables, which are important to attribute this kind of process for certain experiments. All of this information results not in a graphical representation only, but also in an XML structured representation, which is stored then later in our in-memory database. And again, using this description, you can reconstruct this graph for processing in our runtime environment. So let's dig a little bit deeper. How does it look like? You see there are some interesting features in that BPMN as well. You have these annotations like reference genome, HG19 or HG18, which can be used as input parameters, as static input parameters in this case. Certain parameters will be marked with a $sign at the beginning, which need to be fulfilled at a runtime. And then you have these kind of split gateways. This is an AND gateway. That means you will have to go both directions here for processing. So in the end, you will find this individual process strings and bring them together to do further things. This is important to understand because this is an easy way to model the whole stuff. And in the end, it's also more advanced in exchanging this information with other departments, with other colleagues, or document how to do this for the next generation of experiments. So storing this information results in an XML-based structure. XML is a file format which is human readable, and therefore we can have a look at this. And you see it's called XPDL. This is exactly this format for the BPMN structure, and you see certain things like objects here and how they are associated, but also colors, which are not so important for the whole process. And this information is really exchangeable with other folks and also computer readable and understandable to reconstruct. In the database, in our context in the in-memory database, it looks like this. We have two kinds of database tables. One is the models table, where all our predefined models are located, and you see in the middle there's that content attribute, and this content attribute exactly carries this XML structure. And on the right hand side you have this pipelines table, and this pipelines table holds all the individual model instances, so to say. That means if you have certain parameters which are set for one of the models, from the left hand side it's stored on the right hand side for execution and for one experiment. Why is this important? Our approach goes a step further, not only to store the persisted model in the database, but also to keep most of the processing, the data processing, in the database. We have initially talked about the alignment and other tools which are reading and writing from files, and we want to eliminate the bottleneck of the file system. Therefore, you see here on the left-hand side one exemplary process which is used if you use it on a file-based traditional way, and you'll see on the right-hand side the more or less optimized process, which we are using in the memory database. And you see it's much shorter. That's important to see, because certain steps like merging data, sorting data, or splitting up data, this can be easily done as a database transformation. So that means you have an SQL statement, or you have some kind of SQL functionality which can do the same stuff. So you do not need to do it on a file-based structure, but you can build on the expertise which was gathered across the last 3-4 decades in database management systems, and use this kind of technology, which is far more optimized than what you have to do in a file system. And therefore, what we are doing is we have quite a lot of tools available within our in-memory database system. Of course, they are optimized for single read, paired read, and applicant experiments, but also you can incorporate existing tools, these file-based tools, without any adaptation. That means the results will automatically import into the database, which is still a little bit away from the optimum, because the results are still generated in a file-based manner, but then we are using a so-called in-memory database file system, which transfers the data transparently into the database. And on the other side, you can have also the chance to develop highly optimized approaches, like IMDb optimized alignment or variant calling, which do not need to work on files any longer. They use the structures within the database, work on the database structure, and write results again in the database structure. So you have a lot of media breaks which are eliminated, improving the overall throughput. So what's next? Next time we want to learn about how to execute these kinds of pipelines. So therefore we have a runtime environment, our worker framework, which ensures the scalability also if you consider high throughput processing, let's say 1,000 patients per day. And if you have to scale up, you can easily add or remove resources here to the system without the need to reconfigure everything. Therefore, stay tuned. I'm looking forward to see you next time.